how a program can refer to a memory address. Okay, if in absolute code, that means the before the compilation, we already know where to load a program. Okay, so the compiler can generate absolute code. Okay, okay, and any relocation or binding information will be done at linking time. Okay, so after link to all the object module together become an executable binary. The binary can only be loaded into a specific location. Okay. The second passport is dynamically relocatable code. That means the executable image during the load time, they can be loaded to a non-specified place. Okay, and only the during the load time we know where the module to be will be located. Okay, and so the loader need to do something to figure out how to resolve those address problem. Okay, and the third approach is position independent code. Okay, instead of generate absolute code or leave all these unresolved symbol tables or reference binding in loading time. Okay, the position independent code means all the reference generated by compiler are relative to something, okay, to program counter or to specific registers. For example, you use GCC compiler, then with this option, then they will generate this position independent code. Okay, the last approach, and we will discuss later, is that using logic address. So the compiler generate abstract code. Okay, however, by using hardware support, this abstract code is a logic address. Okay, so they all started from position 0 to position maximum. Okay, so each program image or executable image, they all started from location 0 to a maximum. Okay, however, so although the machine CPU will generate reference to absolute location, but this absolute location is a logical, not real memory location. Okay, this logical to physical address mapping was supported by special hardware. Okay, so during the instruction execution time, okay, whenever we generate a reference to memory, before go to the system bus, before the address, logic address go to them, they will translate to real physical address and then go to the memory. So they will get the right memory and so on. Okay, and this special memory or hardware, they will do this automatic translation. Sometimes we call it this kind of hardware module, the memory management unit. The unit depends on hardware design. Some hardware they embedded into the CPU, okay, some as a separate chip, and some included in the CPU chipset module. Okay, it depends on how you organize your chipset hardware and so on. Okay, and so this logical to physical address space, okay, concept, okay, is that a logic address space is bound to a separate physical address space. Okay, and those mapping are done by a spatial memory management unit. Okay, so logic address generated by CPU. Okay, sometimes we call it virtual address. Physical address is the address used or thinned by memory unit. Okay, and this gap, this translation, okay, can be done by a special memory management unit. So in compile time and loading time, address binding, scheme, logic, and physics are the same because they don't need to bind to the physical address. All these compile time, bind loading time, they all bind to a logical address. Okay. Only the execution time address binding scheme, logical and physical address can be different. So during execution, all the reference generated by CPU treated as logic, and then we by MMU they translate this logical address into physical real address in the memory. Yeah. The usually the simplest MMU is they contain only two registers. One for the relocation register, set the base register of this runtime module of the program image. Okay, and a delimitation to specify what's the value reference offset, the range of the offset. Okay, so and so every logic address will automatically added the offset, the relocation register value to generate real memory address. Okay, so user program deal with logical address, never see the real physical address. The physical address is used by the memory unit or memory module only. Okay. Let's see this a simple example of the MMU-based relocatable addressing. CPU generate a logical address. Okay, so the compiler they can use the absolute code mechanism. Okay, and the MMU first check the value of this logical address is less than or equal to limit register. If that's right, then all right. Otherwise, it generates trap because it's an autobound reference. Okay, you reference to outside the range of proper addressing. Okay, if within the range, then the base register value will be added to go to the send to the system bus. The memory module will use this physical address. Okay. So just simple, okay. That's a simplest memory unit. Only two special hardware registers, okay. Okay, so a program linking can be done by static or dynamic. Okay, executable library usually can be generated or linked together by several separately compiled source codes, okay, or with some library functions, okay. So the linker is responsible for combine these file or object modules together and resolve all their external reference and naming problem. Okay, the static linking is the case where a linker resolve all the symbols and include all the code that is needed to run the program within the executable file. Operating system program loader and then load it into memory and run it. So dynamic linking can leave certain libraries and symbols unresolved, but are loaded on demand until they are referenced in runtime. So the dynamic linker usually links the program with some library, pseudo library or stub libraries. Okay, and this stub library will do the actual loading library to and modify the instructions such that subsequent reference to these libraries, they don't always go through this step. Okay, they can directly go to the actual location of the library. Okay, and so and dynamic loading is the subroutine. It's not load until it is called. So by using this way, we may be able to set memory spaces. Okay, unused routine never loaded into the system. Okay, so it's useful when a large amount of code are needed to handle infrequent cases. For example, the error handling routines. Okay, a good software design usually contains a huge number of error handling routines to anticipate possible runtime errors. Okay, but if your program after detailed sort of the debugging, usually this error will not happen very often. So error handling routine is there just in case, but sometimes, most of the time, they never be used. Okay, so those error handling routines, they may occupy a huge memory space, but they are not used during the runtime for most cases. So if possible, we can use dynamic loading mechanism. Then you don't need to load those error handling routine into memory unless they actually been used in some real cases. Okay. So, but and this mechanism can be done purely by application. Okay, we don't need to support by operating system. Okay, can by proper program. The early PC in early PC environment, especially in DOS operating system, a lot of application, because in that time in the early PC ages, the memory is very costly, so it's a rare resource and very expensive. So most of the time, the memory is less than 1 megabyte. Okay, so a program can be easily larger than 1 megabyte. So a good software in that time, there's a lot of dynamic loading mechanism support by application program itself. Okay, so the application usually the application will write a special dynamic loading subroutines in there. So whenever you try to call, so the subroutine call in application, they all go through this dynamic loading module first, and this dynamic loading module will check the status of all those loaded modules, and if the required subroutine is loaded, then call send the request to the subroutine. If the desired the coding code subroutine is not loaded yet, then the dynamic loading stop or module. Okay, they will find out a module which is currently not used, and release that module from the memory, and though required module into the proper locations, and set up this address refer to those newly loaded modules, and then go to the send request to that desired subroutines and so on. Okay, so this can be done by application itself. But of course, this kind of application, the operating system need to allow the application program to be able to do some to use memory for to be able to directly load program into the memory instead of load program modules into memory by calling operating system service. Okay. For shared library, okay, dynamic linking enabled the use of shared libraries. The same block of code may contain a library that can be referenced by multiple processes that needed it, and they are all currently in memory and they are ready to run. Okay, they are competing the CPU simultaneously. So if an unloaded shared library is referenced, program loader will allocate memory and load it from the library file. If a loaded library is referenced, the program loader will replace the process reference to the memory the library was loaded. Okay, so a shared library may be loaded in different memory or at each memory register. Okay, it must be compiled to use relative addressing or position independent code. Okay, the operating system can keep track the reference number of reference to each shared library when the last process that use a shared library terminate. The library is then can be unloaded from the memory to use those memory for other purposes. Okay. Now have all this background about how physical address, logical address, and linking mechanism, dynamic loading, dynamic linking, and shared library. And we can discuss how to efficiently manage the memory. Okay, the simplest approach is was used by the early operating systems, especially for personal computers. Okay, it's we call it single partition multi-programming. Okay, that means the memory only reside two programs. One is operating system, and the other is a running program, a process. Okay, so only a single program loaded in memory at any given time. Okay, the program shared memory is the operating system. Okay, and in general they are set up like this, always in one end, and the program is started from the other end. Okay, and so the actual addressing for this program, this kind of memory management is no problem because all the programs are loaded starting from, for example, location 0, okay, to maximum, okay, until they meet with operating system. Many early systems, those they use this approach. Okay. And to doing the multi-programming, then the operating system need to move if the current program, okay, the running program is using I/O and to reuse the CPU, operating system need to move the current program, running program, back to the disk and load another program which is ready, okay, into the memory. Okay, and so this we call it swapping. Okay, a process can be swapped temporarily out of memory to a backing store, usually is a disk, and plug in data for continuous execution. Okay, so a backing store can usually is a fast disk, and they have big enough to record, store all the memory images of the current running processes or ready processes. Okay, and this baking store, it must have the capability to access this memory images for all the program is currently running. Okay, and this we call it swapping. Okay, you swap a program out and swapping in. Okay, and sometimes we call it low out, low in a swapping mechanism. If the scheduling is based on priority. Okay, so low priority process can be solved up when the high priority process comes in. Okay, and so on. Okay, it's so low out, low in is usually a special name for swapping in priority-based scheduling policies. Okay, so the swapping time is transfer the image program image between the memory and the backend store. Okay, and the time is dependent on the size of the program image. Okay, and a lot of modern systems they use some form of the swapping mechanism. Okay, with their own optimization. Okay, but the basic concept is the same. You swap out a process which is currently not using CPU. Okay, and to use the memory for other purposes. Okay, so operation maintain a ready queue of ready to run process. Okay, and those processes their memory image or memory map maybe on disk or on memory. Okay, for a more advanced operating system, usually the ready queue has two ready queue. One is in memory ready queue. One is in backend store or out of memory ready queue. In memory ready queue means those processes which are occupied by memory, and also ready. Out of memory ready queue means those processes they are ready because they only require CPU, but they are not currently reside in memory because the memory space is there's not enough memory to hold all the ready processes. Okay, so some ready process may in the backend store also. Okay, not in the memory. Okay, so that's the with the swapping mechanism. Okay, dynamic loading mechanism, this become possible. Okay, so the conceptually we have a memory. We have two parts of memory. One is operating system. One part used and another part used by user. Okay, the simplest one is the memory only occupy one program at a time. Then when a program is not using the memory, that means it's waiting while or it did not use CPU, then this process need to be swapped out. Okay, and the operation will stack another process from the backend store and bring it back to the memory. Okay, and with the proper context set and restore mechanism, the context switching mechanism, then the fast data transformation between memory and the backend store, then it's possible we can improve the performance of the memory. Okay, so and so on. Okay, so swapping can be used in single partition. Okay, the memory always keep only one program. Okay, but later because the memory become cheaper, So we have a huge memory from 1 mega to 1 giga. Okay, for example, most of the PC is more than 1 gigabyte of memory. Okay, so it's nonsense to only keep one process in memory at a time. Okay, so it's possible the memory is big enough to keep multiple or several processes at a time. Okay, so the user space part of the memory, we need to separate, store more than one process. Okay, so a possible way is we partition this user part of the memory into multiple fixed size partitions. So divide memory into predefined partition, or sometimes we call it segments. And this partition, they don't need to be same size, because to be able to because some process may have huge memory requirement. There are some process may be small in size. Okay, so with different size is possible. So different kind of process can be in memory at the same time. Okay, so usually a good mix is that a few big partitions and many small partitions get together. So because in average most program or process are not too big, but occasionally you would have some few process they are huge. Okay, the new process get to specific partition which is big enough to hold the incoming process. Okay, and unused memory in the partition is wasted. Okay, so every partition can hold one process, okay, at a time. Instead of the whole memory hold one process, can in here every partition hold one process at a time. So you have, for example, you have 6 partition, then you can hold 6 process in memory with different sizes simultaneously. And if a partition is not is there, but it's not good in big enough for all the waiting process, for all process which is ready, then this memory are wasted. Okay, so unused partition is wasted because it's too small for waiting processes. So, and this kind of memory we call it external fragmentation. Okay, and inside a partition, if a partition has size n, and we assign a process with size less than n, then this partition, after all, okay, this particular process, there are some memory space is wasted because they cannot use. Okay, so this kind of memory waste we call it internal fragmentation. Okay, so inside a partition which is unused is internal fragmentation. Okay, a whole partition is unused. These are external fragmentation. Okay, a process take up a continual region of memory. So this mixed fixed partition and single partition, they are all contiguous allocations. A program can they need to occupy a contiguous region of the memory. Okay, so relocation register or mechanism of MMU, they use 2 registers is enough. Okay, they used to protect each process from each other and change the organization's code and data. Okay, so base register contain the value of smallest physical address. Limit register contain the range of the logical address. Okay. Then also, so for this multiple partition mechanism, we need to have, for example, you have n partition, then we need to have n set of this base register and limit register pairs. Okay, so every set, every pair correspond to recall a process which is occupied in that particular memory partitions. Okay, and CPU can be switching between among these processes which are reside in memory in different partitions. Okay. Because this external fragmentation problem, okay, you have some partition which is wasted because all the waiting process require larger memory size. Okay. To better utilize these memories, another approach is multiple variable partitions. That means a variable memory divided into occupied memory part and unoccupied memory portion. Okay, it depends on the incoming request, the size of the process. Okay, the size of the incoming request, the process size. Okay, and this kind of approach, we have two terms. One is a whole or unused memory portions. Okay, it's a block of variable memories. Okay, and holes of variable size are scattered throughout this memory. Okay, look this example. For example, initially we have three processes in the memory, find A and 2. Okay, they all allocated in this phase in this way, and when process A finished, then it will move out of memory. Okay, and the portion which become original occupied by process A become empty. Okay, so then it's possible we can allocate a smaller process which is size smaller than this whole. Okay, for example, process 9 is allocated just under the process 5 and leave a hole between process 9 and 2. Okay, and then you can allocate another process and so on. So the size of the free memory is dynamically changed. It depends on the allocation sequence. Okay, and so on. Okay, so whenever a process arrives, it's allocated to a hole which is big enough. Okay, and after the allocation, the remaining the part of this hole is still available. Okay, so and operation, as long as operation can keep track all the allocated portion and free portion of the memory, then it's fine. Okay. So the allocation algorithm for these multi-variable partitions, so the partition size, number of this memory, okay, it depends on how this incoming process, their size distribution is so on. Okay, so there's basically three typical algorithms. Okay, to allocate a free space to an incoming process. Okay, the problem will be whenever a request of size n, okay, comes in, we try to find a big enough free partition for these incoming processes. Okay, and remember we said that operation need to keep track all the free holes and allocated part. Okay, the reason to keep track allocated part is when the process finished, this allocated part occupied become free. Okay, so we need to merge this free hole if this free hole is there's a neighbor. Okay, neighboring free hole Okay, there is adjacent free hole. They are their neighbors. Then you may need to merge this free portion to other existing holes to become a bigger one. Okay, and this merging may be merged up or merged down, depends on its neighbor. Or you have 3 hole after occupation. Occupy the partition become free, then maybe 3 adjacent holes need to be merged together. Okay, so always need to keep track, free the partition and occupy the partition also. Okay, so whenever a size n process comes in, okay, we need to allocate a free partition which is big enough. Okay, so the allocation partition may be decided, for example, the distance may be maintained according to the location or according to the size. Okay, and the first free means you search this free list and allocate the first hole which is big enough. Okay, okay, and best free is you allocate the smallest hole like big enough. That means as long as the free list is sorted according to their size. Okay, from by ascending orders of the size. Okay, then the first one will be always the you just search the start from the smaller free partition to the bigger one. So the first one we big enough will be the smallest hole that big enough. Okay, so that's the base fit. Okay, you must either search the entire list if the hole is not sorted by the size. Okay, if it is sorted by size, then the smallest one is the first one you find out which is big enough. Okay, however, after this smallest hole allocated to this newly requested, newly processed, they leave a very small hole, and this very small leftover hole become useless because you never find a process which is smaller than, okay, so small. So this small hole become wasted, and this waste is external fragmentation because the operation keep track but cannot be used. To avoid creating a very small useless hole, okay, the smallest hole may be assigned to the new process as a whole. Okay, so instead of you partition the free the free partition into 2 places, one is occupied and a very small one as a free partition. We just assign the whole free partition to this new process. Okay, and so always did not keep track of those leftover small holes. Okay, but again, we still generate some fragmentation, and this is fragmentation, internal fragment, because now the assignment is bigger than the actual requirement. So they still have a small portion of memory it become useless. Okay, but this useless did not operation did not need to keep track. So the semantic is different. Okay. Although we always some small portion of the memory, but the external fragmentation it require operation to keep track. Internal fragmentation also it's already be assigned to a process, so always did not keep track. It just track the whole part as a use the partition. Okay. Okay. So that's a trade-off. Okay, how small is the small enough? Okay, so parameter for best fit is that usually you need to define this small list, the threshold. So if the level over is too small, what is too small, we need to define that. Okay? And the third approach is worst fit. Okay, we saw this free partition in size in according to size, but in descending order. So the first one is always the biggest hole. Then so you partition the largest hole to two parts, one for the new process and the other part you just rearrange its location, you move to the right place of this free list. Okay. Because you always produce the largest leftover one, so it's possible this largest leftover whole maybe become useful for later usages. Okay, but we need to move this one. Okay, we need to move this largest whole leftover whole to rearrange this sorted list. Okay. So that's time consuming for this allocation. Okay. So in general, by simulation, by practice, experiment, and whatever, the first three and best three they perform better than worst three, and the first three and best three there's no significant difference between in terms of speed. The performance and storage utilization, they are similar. Okay, now OSP and they are better than OSP. Okay. Another approach to for these allocations. Okay, single partition, multiple fixed partition, and multiple variable partitions. Okay, you can use the dynamic the program or process need to be allocated in a contiguous fashion. Okay, in a contiguous fashion, and so every partition has an associated pair of limit and base registers. Okay, so it depends on how many partitions you generated. So operator keep track of occupied partition. So for example, and during this occupied partition list, the data structure will contain the value of limit and base registers. Okay, and when that particular process is in running state, then the MMU, the value, the two register in the MMU will be loaded into the value of this associated with this running process. Okay. Because this contiguous allocation requirements for this partition, multiple partition mechanism. Okay, and some external, either external fragmentation or internal fragmentation may be generated by these mechanisms. Okay, and to avoid this memory requirement for contiguous allocation, and sometimes avoid some external fragmentation. Another approach is that the page-based memory management was proposed. Okay, in this kind of mechanism, the logical address space of a process, they don't need to be contiguous anymore. Okay? When you assign memory to a process, they don't need to be assigned in a contiguous fashion. Okay, in this way is and also the physical memory is also physically they don't need to be contiguous also. Okay, so physical memory, okay, are divided into fixed sized block. We call it frames or page frames or memory frames. In general, frame size it will be set to a power of 2, for example, 12 bytes or 8K bytes. Okay, and logical memory of each process is also divided into blocks of the same size. We call it pages. Okay, the page size and the frame size usually are equivalent, okay, but they can be different, but in general we set this to be equivalent for simple management purpose, okay. But why we use two different terms? Because the semantic are different. Page is referred to the logic addressing space, okay. The frame is referred to physical memories. And then you're doing a mapping, map a logical page to a physical frame. Okay, like that. So, and always keep track all three frames. Okay, which frame are used and which frame are currently not used. Okay, so to run a program of n page, we need to find n free frames to allocate these n frames, n pages. Okay, and these n frames they don't need to be in the contiguous fashion, okay? As long as we can map, we maintain a mapping table with n entries, n page, then we will have an entry, and the entry in the map, for example, the first page maybe stored in the cell frames, okay, and the second page maybe stored in 6 frames of physical memory, and so on, okay. So a page table then is used to translate logical address to physical address instead of by using the simple base and limitation. Now we need to have a table, okay. So for each page, because logic page they can map to any physical frame, okay. So instead of simple register, then now we need to have a table, okay. And by using this mechanism, external fragment can be eliminated, okay, in the sense that as long as the incoming process, if incoming process require n pages, as long as there are n free frames, then we can allocate. We don't need to require those n frames to be contiguous, okay. So these n frames can be scattered around the physical memory. So as long as the total number of free frames are larger than the incoming request, then the allocation can be successful. Okay. So external fragmentation can be eliminated, because unless all the processes they require size number of frames larger than the currently available frames, okay? But internal fragmenting still existed, okay? Because the last page, okay, of a process usually is not the full page, okay? In general, or in average, every process would have a half page internal fragmentation, because it's almost impossible a process. The required memory for a parity is just exactly n pages. Okay, in general, is the last page will not be fully utilized. Okay, so you have some, but we allocate in the fixed size blocks in page. Okay, so last page always have some unused memory. Those are internal fragmentations. Okay. So this page translation mechanism will work something like this. The page table can be stored in the memory management unit. Okay. The CPU generally logical address of page number with an offset. Okay. Then this page number is used as an index to find out the mapping, the real physical location of this physical frame. So the frame number will be retrieved, replace this. So the physical address will be FD concatenated with D. Okay, the offset will be the same. Okay, and this physical address sent to the physical memory, and the memory will retrieve. Okay. Okay. So that's the simple page translation. Okay. And this page table can be implemented. First, they must be kept in operating system, okay, for every process. Okay, in general, this page table can be kept associated with the PCB. Okay, program control block. Okay, and there will have a page table base register point to the page table. Okay, the starting position of page table, and the length register to indicate the size of the page table. Okay, how many entries of this table. Okay, and so every data instruction will require 2 memory access. Okay, if the page table is kept in memory and without any special hardware support for this translation, then we for every memory access to execute a memory access instruction, okay, we require 2 real memory access, one to the page table to the translation, and then one to the real data, okay, or instructions, okay. So the whole process will become half. Okay, the CPU, although the CPU may be fast, okay, for example, the CPU clock may be in some speed, then the real clock will be slowed down by half, okay, because one memory access generate 2 real memory access. Okay, the 2 memory access problem can be solved by using special fast search hardware cache. Sometimes we call it associative memory or translation look aside buffer TLB, okay, or access associative memory. Some TLB store address space identifier in each entries also. Okay, and this TLB cache, okay, can be stored in the MMU. Okay. The paging mechanism, page with TLB. Okay, TLB is a cache that usually you only store frequently used page entries. For example, because the locality problem, when you run a program, in general, a real application program usually contain a sequence of loops. Okay, when inside a particular loop, executing codes inside a particular loop, those only those related to this particular loop, those pages which related to this particular page loops are needed during the execution time of the loop. Okay, so not all the pages are needed. Okay, in the same time. Or okay, and this loop. When the loop finished, the program execution will go to another loop, and so on. Okay, so only those frequently or currently used pages entries will need to be maintained. And so a TLB cache can be used to hold those currently required page entries. Okay, for example, then this TLB will contain at least 2 attributes, 2 fields. One is the page number, another one is frame number. Okay, and usually this TLB cache has a parallel search capability. So you send out this page number, and all the entries will search in parallel, okay, simultaneously. If any of the page was found in the TLB, then the corresponding frame number will be sent out. Okay. And this we call TLB hit if we can find the logical page number in this TLB cache. So the corresponding frame number will be automatically pushed out and replace the physical address part. Okay. And if the TLB did not hit then we call TLB miss. Then this page, then we go back to these two memory access. Okay, and then we need to go to the page table in the memory and use P as an index to retrieve this F frame number, and then real physical address will go up. Okay, that's all. Okay. So depends on the TLB hit or miss. Okay, the memory X time will be different. Okay, so if the TLB cache the hit ratio of TLB is high enough, then the effective memory X time will be reduced dramatically. Okay. Here is a simple calculation of effective access time with TLB. Okay. If we assume that TLB access time is 10 to -6 seconds, okay, as microseconds, okay, the memory access time is in milliseconds, okay, it's just an assumption, okay, but in general, this the order of the TLB access time and the memory is in this thousands, okay, 3/4, and the hit ratio is 90%, for example. A memory access may lead to a TLB hit, then we require 1 TLB search plus 1 memory access, and otherwise we require 1 TLB search plus 2 memory access. So the effective memory access time or expected memory access time become 0.9 times 10 to the -6 plus 10 to the -3 plus 0.1 times 10 to the -6 plus 2 times 10 to the -3. So we put them together with 10 to the -6 plus 1.1 times 10 to the -3 is because 10 to the -6 is ignorable compared to 10 to the -3. So it's very close to 1.1 of the memory access time. So that means if the in this situation, if the hit ratio is 90%, then the downgrade of the memory access, the effective memory access will downgrade only 10%. Okay, it becomes the original, the 1.1, 110% of the original memory access time. Okay, so it's almost it's more or less something like this. Okay. If the page table is too large, okay, for example, the page may contain more than 1 page. For example, the page table itself is large enough to need to be occupied more than 1 page. Then the page table itself can be paged again. Okay, so most processes use only a small part of their address space. Keep entire page table become wasteful. For example, for 22-bit system with 4 KB pages, then we have a 20-bit page table. That means the entire page table may contain 2 to the power of 20 entries. Okay. Because the possible program size will be so huge. Okay. So to deal with large address space, large logical address space, okay, a program may have contain a large address space. Then we need to the page table entries there's too many page table entry to put in just single physical frames. Okay, so we may need to separate page table into different frames. Okay, so the way to maintain a huge logic pages will be hierarchical pages. They use multi-level page tables, and another way is hash the page table or inverted page tables. Let's see what is. Hierarchical paging is something like we break up the logical address space into multiple page tables. A simple technique is a two-label page table. So for example, again, a 32-bit logical address or 1K page size. Then we divide this into a 22-bit page number and 10-bit page offsets. And the page number can then be paging into a 12-bit outer page number and 10-bit inner page numbers. So we have an outer page table, okay, and every page table has a 10-bit inner page numbers. Okay, so this when page mapping, we go through the outer page table, find out the inner page table number, and then go to the, so one memory access become 3 memory access. Okay, unless we can cache the outer page table and the recently used outer page table, the entries currently used, and the entry currently used for the inner page tables, or in the TLB. Okay, and this mapping can be done in TLB by go through 2 TLB searches. Okay, if hit, then the memory access become can be okay, and so on. Okay. So address translation in two-label paging will be something like a logic address contains 3 parts: P1, P2, and the end offset. P1 used for the outer page table to find out the inner page table, the starting address, the page number or the frame number or inner page table. That's P2. Okay, and then use P2 to search the inner page table to find out the real frame number. Okay. And then the D as an offset for this thread. Okay. Hash the page table is that usually used for address logic address is larger than 32 bits. Okay. So the virtual page number is hashed into a page table. Okay. So we use a hash function. The hash this virtual page number into a small fixed sized hash table. Okay, and this table contains a chain of elements hashed into the same locations. Okay, if the logical page number after hash lay into the same place, and this virtual page number are compared in this chain search for a match. If a match found, the corresponding physical frame number is extracted. Okay. Of course, to make this hash table useful, the hash table and corresponding chains need to be stored in a fast MMU or similar or fast memory modules. Okay, to reduce this mapping translations. Okay. Inverted page table can be used. Okay, instead of the philosophy behind is like, because the physical frame number usually physical frame is fixed. Okay, the logical page table may be varying in size because different program may have different logical page table size. Okay, but the physical frame is fixed. The number of physical frame is fixed. Okay, so instead of maintain this logical page table, we can maintain the inverted page table. Instead, the map from page to frame, we recall the logical page and the process information for each physical frames. Okay, use the physical frame become to. Okay, the ICE entry content which page is located in this frame I. Okay, so and for this inverted page table, we also need to keep track the page, the process ID also. Okay, so this usually inverted page table contain at least two fields. One is the process ID, another one is the page numbers. Okay, so and this can reduce the memory needed to store page tables in the memory. Okay, but they may increase time to search the table when the page reference occurs. Okay. And also the hash table can also be used to limit the search to one or at the most a few page table entries. Okay. So this for inverted page table is that CPU generate logical address. Okay, and this logical address contain page number and PID. Okay, and we use PID and page number to search this inverted page table. Okay, and okay, and return the index will be the physical frame number. Okay, will return and go to the physical memory. Okay, because the size of inverted page table is fixed, so they can be located in memory in the fixed location of the operating system, the memory. Okay, this search. And to make the search faster, either the TLB was used, okay, for inverted page table, okay, or otherwise, this hash table can be used also. Okay. Now we take a risk.